Imagine a structure so grand, so ambitious, that it stretches across a mile-wide strait. The Tacoma Narrows Bridge was a marvel of modern engineering, a testament to human ingenuity and ambition. It was designed to connect communities, to bring people closer together, and to stand as a symbol of progress and innovation. Now picture that structure, twisting, writhing, and ultimately collapsing under the force of the wind. The bridge, which was supposed to be a beacon of hope and connectivity, became a nightmarish scene of destruction and chaos. The wind, an invisible yet powerful force, turned the bridge into a writhing serpent, a spectacle that was both mesmerizing and terrifying. This wasn't a scene from a disaster movie, this was the reality of the Tacoma Narrows Bridge collapse, a stark reminder that even the most impressive feats of engineering can be humbled by the forces of nature. The collapse was not just a structural failure, it was a humbling experience for the engineering community, a lesson in the importance of understanding the environment in which we build. On November 7, 1940, the Galloping Gertie, as the bridge was affectionately known, danced its way into history, not for its elegance, but for the catastrophic failure that sent shockwaves through the engineering world. The bridge's undulating movements, caused by aeroelastic flutter, were a sight to behold, but they were also a prelude to disaster. This wasn't just a bridge collapsing, it was a symbol of human ingenuity crumbling before our eyes. The sight of the bridge falling into the water was a poignant reminder of our limitations and the need for humility in the face of nature's power. The reactions of the people who witnessed the collapse were a mix of shock, disbelief, and a sobering realization of the fragility of human creations. The Tacoma Narrows Bridge, once a symbol of progress and innovation, became a potent symbol of the importance of understanding and respecting the natural world. The bridge's collapse was a turning point in engineering, leading to new research and advancements in the field of aerodynamics and structural engineering. It taught us that progress must be tempered with caution and respect for the forces we seek to control. It serves as a stark reminder that we, as engineers and as a species, must always strive to learn from our mistakes and build with a deep respect for the forces we seek to tame. The lessons learned from the Tacoma Narrows Bridge collapse continue to influence modern engineering practices, ensuring that such a tragedy never happens again. As we look to the future, we must remember the past and build with wisdom and foresight. The Tacoma Narrows Bridge, completed in July 1940, was a source of immense pride. It was a symbol of modern engineering and a testament to human ingenuity. The bridge was not just a structure, it was a beacon of progress and a promise of a connected future. Connecting Tacoma to the Kitsap Peninsula, it was the third longest suspension bridge in the world at the time. This impressive feat of engineering spanned 2,800 feet, making it a critical link for transportation and commerce in the region. Its slender design, intended to be aesthetically pleasing and cost-effective, was a point of both admiration and concern. Engineers marveled at its sleek lines and modern look, but some whispered about potential issues that might arise from such an innovative design. Costing a then whopping $6.4 million, which is over $120 million today, the bridge was heralded as a marvel of engineering. The investment was seen as a bold step towards future growth and development, a necessary expense for the promise of progress. Its 2,800-foot main span soared gracefully over the Puget Sound, a testament to human ingenuity. The bridge's elegant silhouette against the backdrop of the water was a sight to behold, capturing the imagination of all who saw it. Little did anyone know, hidden within this elegant design lay a fatal flaw, a vulnerability that would soon reveal itself in the most dramatic way imaginable. The very elements that made the bridge a marvel would also contribute to its downfall. The bridge, meant to connect communities and drive progress, would soon become a symbol of the delicate balance between ambition and the unforgiving laws of physics. Its collapse would serve as a stark reminder that even the most advanced engineering can be humbled by nature's forces. From the very beginning, the Tacoma Narrows Bridge exhibited strange behavior. Its deck, notoriously nicknamed Galloping Gertie, would oscillate vertically, even in relatively mild winds. Local newspapers even ran humorous stories about the bridge's unusual bounce, unaware of the danger lurking beneath this seemingly harmless quirk. Motorists reported feeling seasick as their cars bounced along the undulating roadway. Some even claim to have seen cars ahead disappear momentarily as the bridge dipped and rose. These were not isolated incidents, they were consistent and increasingly alarming signs that something was amiss. Engineers, initially dismissive, began to take notice, but the bridge, already open to traffic, was a source of local pride and economic importance. The pressure to keep it open, despite the growing concerns, was immense. The Tacoma Narrows Bridge's demise was a tragic interplay of physics and engineering. The bridge's downfall was ultimately the science and stability be controlled. Section 5. The day the bridge fell down, a timeline of disaster, November 7th, 1940, dawned like any other day. The city of Tacoma was waking up to a crisp autumn morning, with residents going about their usual routines, unaware of the impending catastrophe. But for the Tacoma Narrows Bridge, it would be a day etched in history for all the wrong reasons. The bridge, often referred to as Galloping Gertie, due to its tendency to sway in the wind, was about to face its ultimate test. At around 7 o'clock in the morning, with winds already gusting at 40 miles per hour, the bridge began its fateful dance. The wind, a seemingly benign force, was about to unleash its full fury on the structure. The familiar undulations were now violent, twisting motions that sent ripples down its length. The bridge, which had been a marvel of modern engineering, was now a terrifying sight to behold. The bridge, designed to withstand winds far higher, was no match for the invisible force that gripped it. Engineers had not anticipated the phenomenon of aero-elastic flutter, which was now causing the bridge to twist uncontrollably. By 10 o'clock in the morning, the bridge's movements were so severe that authorities closed it to traffic. The decision was made just in time, as the structure's integrity was rapidly deteriorating. Witnesses described the bridge as undulating like a snake and rippling like a sheet in the wind. The sight was both mesmerizing and horrifying, a dance of destruction that seemed almost surreal. The bridge's groan, a deep guttural sound, echoed across the water, a testament to the immense forces at play. It was as if the bridge itself was crying out in agony, a final plea before its inevitable demise. At 11:02 in the morning, with a final agonizing groan, the center span of the Tacoma Narrows Bridge gave way, crashing into the waters below. The collapse was sudden and dramatic, a catastrophic end to the bridge's short life. The iconic image of the bridge, twisted and broken, became a stark reminder of the power of nature and the importance of learning from our engineering failures. The disaster led to significant advancements in bridge design and aerodynamics, ensuring that such a tragedy would never happen again. Section 6. Learning from tragedy, a turning point in bridge design. The Tacoma Narrows Bridge collapse was a pivotal moment in the history of bridge engineering. It forced engineers to re-evaluate their assumptions about bridge design and to take into account the often unpredictable forces of nature. The collapse ushered in a new era of bridge design, one that placed paramount importance on understanding and mitigating the effects of wind. Wind tunnel testing, a technique used to study the effects of wind on scaled-down models, became a standard practice in bridge design. Engineers began to incorporate aerodynamic considerations into their designs, moving away from the aesthetically pleasing but inherently unstable designs of the past. The Tacoma Narrows Bridge, though a tragedy, became an invaluable case study, a stark reminder that even the most impressive feats of engineering can be humbled by the forces of nature. Section 7. Echoes of Tacoma, modern engineering, and the quest for safety. The lessons learned from the Tacoma Narrows Bridge collapse continue to resonate in modern engineering. Today, bridges are designed with a much deeper understanding of aerodynamics and structural dynamics. The use of computer modeling and advanced materials allows engineers to create bridges that are not only stronger but also more resistant to vibrations and wind-induced oscillations. The legacy of the Tacoma Narrows Bridge is not just about the collapse, it's about the transformative impact it had on the field of engineering. It serves as a constant reminder that innovation must go hand in hand with a deep respect for the natural world and a commitment to learning from our mistakes. The collapse spurred a revolution in bridge design and safety standards, forever changing the way we build and interact with our built environment. Section 8. The future of building beyond the Tacoma Narrows. As we look to the future of engineering, the lessons of the Tacoma Narrows Bridge remain as relevant as ever. We live in an era of increasingly ambitious construction projects pushing the boundaries of what's possible. From towering skyscrapers to underwater tunnels, we are constantly striving to overcome new engineering challenges, but the Tacoma Narrows Bridge stands as a silent sentinel, reminding us that progress without a deep understanding of the forces at play can have disastrous consequences. As we continue to innovate and build, we must carry with us the lessons of the past, ensuring that our structures are not only impressive feats of engineering, but also testaments to our respect for the delicate balance between human ambition and the unforgiving laws of nature.